In your data career, you will need to master two pillars of mathematics: linear algebra and statistics. In this video, I will cover linear algebra. I will focus more on the concepts and not on the calculations. For this first video, I will talk about vectors, matrices, and their properties. Let's start with a vector. This is a vector. It is common practice to have them as a column and not as a row. Think of a vector not simply as a collection of numbers, which is what you see right now on the screen, but as an object that lives in a space with a given dimension and is pointing in one direction. For example, here in 2D or in a 3D plane. So the next time you see a vector with 5 numbers, think of it as an object in a 5-dimensional space. The space where many vectors of the same dimension can live, like this, is called vector space. And each vector space has two operations: addition and multiplication by a scalar. So addition, here we have 3 plus 1, 4, 5 plus 2, 7, 2 plus 4, 6, and the scalar multiplication by a number, 5 times 1, 5, 5 minus 5. By a scalar, I mean a number. Here comes the first important concept you should always remember. A linear combination of vectors is a weighted sum of vectors. So each vector is multiplied by a scalar and then they are summed together. If there is a combination of scalars that make the sum result in the zero vector, so for example here instead of 3, 2, and 5, we have A, B, and C. There's a combination of A, B, and C that will result in 0, 0, 0, 0. Then the vectors are dependent. If the only combination of scalars that result in a zero vector is each scalar being a 0, so A, B, and C equals to 0, 0, 0, this being the only way to get a zero vector, then the vectors are linearly independent. A set of independent vectors can generate a vector space. What does this mean? That with these vectors, you can combine them and be able to represent all possible vectors that belong to the vector space. And if there is no smaller set of vectors that spans the vector space, we call the vectors the basis of the vector space. For example, you are used to these bases in 3D, 1, 0, 0, 0, 1, 0, and 0, 0, 1. But this is not the only basis on 3D. Check out this one, for example. This one has 0, 1, 0, 0, 1, 1, 0, and 1, 1, 1. It's also a basis in 3D. Note that the dimension of the vector space equals the numbers of basis vectors, in this case, 3. So until now we have talked about addition and scalar multiplication. But what about multiplication between vectors? Vector multiplication is actually not defined in a vector space. Surprise, surprise. But I bet you remember multiplying vectors. And yes, this exists, but only when we consider vectors as matrices of size m rows and 1 column. More on vector multiplication later. Let me first introduce you to matrices. So if a vector can be seen as an object with m rows and 1 column, what is a matrix of size m rows and n columns? Well, you guess it, a collection of vectors, n vectors. From now on, I want you to see a matrix and think of it as a collection of vectors instead of just simply columns. So, n vectors with m elements. So a collection of happy vectors living in a vector space of dimension m. As with vectors, matrices can be summed and multiplied by a scalar. For example, here we can sum them element by element or multiply them by a scalar. But what about multiplication? When you think of matrix multiplication, what is the first thing that comes into your mind? Probably your brain will remember the set of rules you were taught to apply matrix multiplication. First row of the matrix times the vector or what you're multiplying with, and we get the first element, and so on, and we get a result. Cool, right? Well, not really. Since you only remember a simple calculation and not the purpose of why are we doing matrix multiplication, I'm going to present to you two possible multiplications of matrices. The first one, the matrix vector multiplication. By multiplying a matrix A times a vector x of n elements, we obtain a new vector of m elements. What happened? The multiplication with the matrix is a linear transformation from an m-dimensional space to an m-dimensional space. And what is this new vector? It's a linear combination of the columns of A. This is very important, and I repeat it. The new created vector is a linear combination of the columns of A. So here, B is a linear combination of the first, second, until n columns of A, given these scalars of x. So if you look at it like this, x1 times the first vector or column, x2 times the second column, and it's a linear combination. So every time you see a multiplication of a matrix times a vector, think of a linear combination of the columns of the matrix. The columns of A create actually a vector space and transform vectors from dimension n, which was x, to dimension m. Not all dimensions, x dimension 2. Not all the matrices will change dimensions. Square matrices, so n equals to m, leave the vector in the same space, but will probably create a rotation or deformation of the original vector. There's even a special matrix that leaves the vector untouched, and that is the identity matrix. It is a collection of ones in the diagonal of the matrix, so that multiplying the identity matrix times a vector, you would get the same vector, 3, 2, 1. What if the matrix is just one vector? In this case, it is a vector-vector multiplication known as inner product, which results in a number and is related to the projection of one vector on another, which is kind of similar to the idea of a transformation when we had the complete matrix. On the next video of this series, I will explore more about this important multiplication. In this case, it multiplies each element and sums them up. 3 times 1 plus 2 times 2 plus 4 times 3, this is equal to 19. We already looked at matrix vector multiplication. Let's look at another kind of multiplication, the matrix multiplication. In this case, we have A and C, we have two matrices that are being multiplied, and we are obtaining a new matrix B. In this case, for the product B equals A times C, each column of B is a linear combination of the columns of A. So, the first column is a combination of all columns of A determined by the coefficients of the first columns of C. Let's look at it. So, if we see the matrix multiplication, B having each of it as a column, A all of them as columns, and C all of them as columns again, as collection of vectors, the first result, the first column of B, B1, we have it here, it's equal to the matrix vector multiplication of all the columns in A times the first column of C, and so on and so forth. So it's a generalization of matrix vector multiplication. A special matrix multiplication is the outer product, which is a product of an m-dimensional column vector with an n-dimensional row vector, which results in a matrix of rank 1. What is rank? Rank is the number of linearly independent columns of rows, and the dimension of the vector space that is spanned by this matrix is equal to the rank of the matrix. A matrix with only independent columns has a full rank, and if apart from this it is a square matrix, this matrix is invertible. What does invertible mean? Well, let's talk about the inverse. The inverse of a matrix, and we can write it as -1. A minus 1 is the inverse of A. When we multiply the matrix times its inverse, you'll get as a result the identity matrix. So it helps us to solve a linear system of equations. For example, if you have this linear system of equation B equals A times X, you can solve it by multiplying both sides by the inverse. This side, then this side. Here we get the identity matrix. And the result, we have X when X was the unknown. We can get it just by multiplying the result, B, times the inverse of the matrix. If you are a little bit dubious of what a system of linear equation is, I recommend you to look at the references below. Apart from the inverse, there is another important matrix property called the transpose. The transpose of A is a matrix that we obtain by mirroring A on its main diagonal. This is the main diagonal and it's mirrored. For example, the transpose, which we call T, of this matrix 3, 2, 1, 0 is the same diagonally, just the elements are mirrored. And a vector, the transpose of a vector, is simply the row vector, from the column to a row vector. Let's look at some of the important properties of the transpose and the inverse. Here I list them. We have A transpose equals to the original matrix. Then the sum of two matrix transposes equals to the transpose of the first plus the transpose of the second. The multiplication of AB transpose is the same as B transpose times A. And the inverse of the transpose is the same as the inverse of the transpose of the inverse. So they're interchangeable. And the last property is the inverse of A times V equals V inverse times A inverse. Lots of maths, right? I recommend you to keep these concepts fresh, since you will need them in the future for understanding the complicated machine learning algorithms.